Hi, Rashid here. Welcome to my channel, Colorado Chip Design Academy. Today's video is going to be about some of the building blocks of sequential elements or our basic sequential circuit that we study, latch and flip-flop. Flip-flop will be the key one that I'll be using most of the time. Just like combinational circuits, uh, once we learned about basic gates, then we started making some bigger circuit with those gates. Now, flip-flop is also made up of gates. And when I do videos on CMOS design and I go and look inside different combinations blocks and sequential blocks and look inside how they are created with different combination of NMOS and PMOS transistors, you will understand that. So within flip-flop, you also have gates. But we create another abstraction layer on top of those, and we call latch and sequential elements. So a next abstraction level, I should say, is now on top of sequential building blocks. On top of the sequential element, which is flip-flop, how to build some next level building blocks. I have two listed here. Another one is actually that I plan to cover after these two. Those are state machines. Not in this videos, but in future videos. And we will see today how counters are created, because counter is a pretty critical part of any digital circuit. Whether you start from programming, you always have variable that you need to count. So let's see how we can create that, and that should not be a difficult thing because you have already studied the basics. Then shift register we have used few times during the multiplication and division, so it's nice to see how those are made. Then states, that will I explain more in the future video about that, and that's also a very key component of digital circuits. All right, let's get started into counter. Pretty simple. Well, the way we make a counter is, this is our friend flip-flop that we already studied. Here I just laid it down instead of vertical. I could have drawn it vertical, but I drew it like this. Makes more sense if I put this ALU at the top, or this adder at the top. I prefer this thing. And then, okay, core elements or core connections. Remember flip-flop, remember it has a D input, remember it has a Q output, then it has clock pin, and it's on rise or fall. There is no bubble here, so that means this is a rise edge flip-flop. Then it has a reset in it, and you remember the functionality of reset. It will put output into whatever reset condition is, which in this case is 0 0, all 0. This is a 4-bit. I forgot about that. And here how we say that. Here I already mentioned 4-bit. So the setting here, you can pretty much guess this. This is our higher level kind of algorithm. Is when, first of all, if reset signal comes, then Q, which is 4-bit. So remember, these are actually 4 individual flip-flops, but I'm just using this notation, and this register is a bank of 4 bits. But to explain it more easily, I'm just trying a 1 and putting this slash with 4. So the first priority is reset. If reset comes, Q is 0 0 0 0. If reset, this is a reset 1. So when reset is 1, this will go into 0 0 0 0. If reset is not 1, then it's a normal operation. And what's a normal operation? On every rise edge of the clock, this input will go to this input. So whatever the output of this adder will go to the output. So let's start with 0 0 0, and this output is fed back to the adder, one of the inputs. On the other adder inputs, we have fixed it with 0001. You can also say that we have a register here which has this value initialized. So what happens now? 000, and when 0 comes here, 0 plus 1 is 1 sitting here. And on next rise edge of the clock, when there is no reset, okay, this 1 goes here. Then 1 goes here, 1 plus 1, 2. 2 is sitting here, 2 doesn't go here until on the next rise edge. So in this way, if it's a 4-bit and you know that, okay, 4-bit, we will have this sequence. Okay, and so on all the way this. So do you remember what was this? The weights 8, 4, 2, 1. So it starts with 0 and goes all the way to 15. You add one more, it goes back to 0. There's a carry out of 1, you discard that. So it basically on top of this, it takes you back to this state. So this is our friend counter. So this is one. Sometime you will just, what you will do is you will just say, all right, this is my reset, I should say RT, and this is Q, and should I put maybe reset somewhere else? This is clock, and I say this is my counter. So instead of drawing this, I would use actually this. So you can use some block diagram to represent it. Okay, you got it? Let's go to the second one. Shift register. If you remember, during ALU, when we were talking about multiplication, you can watch those videos. We have to shift the values from here to here. On every, there was a algorithm that, okay, if the most significant bit is this, then you shift them. Shift them when they are, okay, let's hold there. So shift them. So shift is, okay, you have, again, I'm just assuming our bus is, that bus is 4-bit. Okay, which means that individual 4 bits are there. And what happening here, the first input D, and this side now flip-flop is going from right to left. D input Q, D input Q, D Q, D Q. So this bit when comes, let's say is 0 initially, and this thing is 1. So after we have a rise edge of the clock, this one, since all the flip-flops are, there's no bubble here, it means they will move data from here to here on the rise edge of the clock. So after the first clock, after this here, we will have 0, 0, 0, 1, and it's the next value, and whatever it is. So on rise edge of the clock, this, on next rise edge, it will go here. I'm just assuming more zeros are coming. On the next one, it will go here. So on every cycle, that 1 is moving on. So I guess that is clear, right? Pretty straightforward. I guess we had a more difficult building blocks like multipliers, adders for the combinational case, but sequential is simple. This can also be used. So I think if you look at initially, it's gonna fit here. Oh, let's fit here. So you know that initially we are moving here, but at one particular time when we move here, we also need to extract the parallel data. So you can really connect each of the output to a line, and that 4-bit coming in individually shifts, but at the right time we just take that output. That is a practical situation. Another one, okay, this one is called serial to parallel. Okay, you're moving serially, but at some point of time you can take it out. This is another circuit, actually a similar circuit, just like you're shifting the values from right to left on rise edge of the clock. I'm not putting any reset here, but maybe there's a reset, maybe there isn't. Ideally, you want a reset because, see, when first time you switch on the power, you really want to make sure your state of the flip-flop will be in a particular state, 0 or 1, like not uninitialized. Maybe in some cases hardware doesn't need that, but in most cases we need it. And that would be always nice to have reset. But when you put a reset, you need additional gates as part of the flip-flops, so flip-flop gets bigger. So those are the things as a designer you need to be aware of. But what I want to mention here is sometime let's say these values are coming. I think that's a good example. Let's say what? Let's say here you have multiplexer. Multiplexer, as you know, gives an option to direct different data into it. Now what I'm trying to do here, what if it's an X1? Now in another serial one, we want to lower this value. So what happens is, here is a control, CTR or control. When control is 1, we always select, we are initializing and kind of you can think of with these values. When it's 1, we are not taking the serial output from the previous stage. Instead, we're taking a new value. So when control is 1, basically we're loading a new value onto this 4-bit register. If it's not 1, that's a normal thing, which is 0. When 0, this goes in. Right? So interesting, isn't it? Here is a parallel to serial. Before we have serial to parallel. So you can play with sequential circuits, sequential building blocks for different requirements of your hardware. Okay, I think that's all I wanted to say today. Yeah, hopefully that was easy. If you have any question, let me know. Thanks so much. See you next time.